all doing well and looking forward to the exam. So let's carry on. Would you like to come out, Josh?
Yes, I just need to hit start. It's a massive delay. That should be live. Yep, that's good.
Cool, so I think you can see a question on this side of the board. Have a little think about what's going on. So there's a question about linear equations and reducing using Gaussian elimination, and you need to find out that there are infinitely many solutions and then find under a certain constraint what the number of solutions are.
So maybe before we start the question, in case you haven't seen it yet, and for those of you who don't know me, I was the lecturer for 1031 last year, so I'm stepping in this year to help do this live stream. So there is a document which is on the Moodle, if you go to the exam preparation tab, which has a link to the last year's exam, which we're going to talk about now. And it had this good guideline for presentation, because the marking for this exam is going to be different from other first year exams you may have done, where in other courses we tend to just worry about whether or not you show that you know the technique, you're getting the technique right. Here we also want you to present it well. So there are a few rules here. A good one is that you should make sure you're using notation correctly. So if you want to use some notation, make sure you're actually using it in the way it's intended to be made. I know the biggest pet peeve of Jonathan, who can't unfortunately be here today, is students using equal signs where they don't actually mean equal signs. So here we're talking about being numerically equal on both sides. And also, if you're just making an approximation, we kind of like it if you make a symbol like this, the approximation symbol.
So for example, let's say a third and 0.33 this is not true.
No.
But you could potentially write this down.
Yeah. I guess for mathematicians, equal really means the two things are the same. These are not the same. There is a difference between them. But numerically, they are approximately the same to a useful... it's useful to think of these as being very close. Since you are marked on presentation, you probably shouldn't start any of your sentences with an equation. It's kind of it doesn't look good. You should start by explaining or just have some linking words to sort of try and do that. So we'll try and do that when we're presenting our solutions today. Make sure you do state your conclusions. The questions are asking you to show something, so at the end you should conclude to say what you have actually shown. There was, I think, a bit of a mistake in the last, a poor design in the last exam, and I didn't design this year's exam, so I'm not sure if it's here too, but in the last exam we actually defined all the variables for you, and I would have preferred if students had to define variables themselves. So it does say here, define your variables. That actually wasn't really much of an issue. Or if they were already defined in the text, try and let the reader know. Try and make the assumption that this person is reading it without really looking at the question. They're just reading to see what you're explaining. If they have to keep going back to the question to get information, that's maybe not good presentation. And your answer shouldn't look like rough work. There's actually only... before we switched to this mastery system, it used to be 4 questions. Now it's down to 2 question booklets. And you can ask for a question booklet for rough working, but there is space for rough working at the end. So do your rough working elsewhere and then try and present it nicely. Present your answers in logical order. So again, that's pretty much, don't make it look like rough working. And make it clear if you're using information where the information comes from. So mostly just say if you're getting information from the text, or if you're introducing something you learned in the course, just let us know where it's coming from, I guess. So that's the generic advice. So if the exam is like last year's, the questions will actually have the marks shown on the thing. They'll actually show you, and each question is worth 15 marks each, with 5 marks for presentations. That's a total of 20. So you'll be marked on presentation on each of the question sets separately. So mostly, from last year, we mostly came down to looking at, was your explanation good and was your notation usage good? That was the main thing we were looking for. So maybe I'll get started on this question.
Yeah, go for it. Yeah.
Right.
Do you want me to get out of the way?
That might be
okay.
easiest.
I might do that.
Could you just hit Alt-Tab to switch to the OBS view? Because this delayed view is a little bit confusing sometimes. Yeah, so that's so I can see myself live. So, well, maybe the other view is better so you can watch the chat.
Yeah, I'll watch the chat.
Okay. So yeah, please do try and make comments in the chat. I can see that there are about 17 people watching now. So if you want to ask any questions or you have any criticism for what I'm doing, it's what we're doing. It's good to let us know. Okay, so one of the things about these questions is they are quite wordy. So there's going to be a lot of information conveyed in words, and you'll have to get that information out. So the first one's quite nice. It does give you this table, and it does give you totals. Right. So yeah, they've already given us the notation, but I might just reiterate what the notation was, just so whoever's reading what I'm about to write doesn't have to go look at the question again. The price of pick this up. So here I'm just really restating what the question already gave me. So the notation we're using, so each of these has a price, and we're going to call these prices X, Y, and Z respectively. So the table we have actually, well, the table and the text actually tell us the following totals. We know how many items were sold per month, and we know what the total for each of those months were. So the total sales in, let's say, so the first month was March. So the total sales in March can be expressed as, alright, well, they sold 10 toy cars, so they get 10x profit from that, or they got 10x money from that. They sold 6 toy trains. Oh, sorry, is it ships and trains? Yeah, sorry, 6 toy ships and 5 toy trains. So this just represents how much money they would have gotten from selling those items in March, and we are told that in March they received $210. So this is clearly, so yeah, if you were doing the exam and you just wrote down this
Josh,
equation.
Do you want to correct that 5y equals, it's 5z, yes?
5z, yeah, sorry, there's too many y's. Thank you. I watch myself. Yeah, so if you had just sort of maybe ignored the text and written down this is good technique, but it's not good presentation because you haven't explained what this even means. So there does need to be some explanation leading up to this. Now, once we've established this, it's fairly, I might just say, likewise, for the other 2 months, so April and May. We get 2 more equations. So in April, they had 20x toy cars. They had, oh sorry, the money they get is 20x. They get 16y and 12z. And their total for that month was 488. That and you get another equation which is 10x plus 14y plus 9z, and the total for that month was 346. Now you do have to make sure you're getting these numbers right, because with linear equations, if you make mistakes, the solution will change quite drastically. And here it's actually set up to have very nice possible solutions. I'll just double check my numbers. That's 10, 6 and 5 goes to 210. 20, 16 and 12 goes to 488. And 10, 14, 9, 3, 4, 6. So yes, it does seem to be the right set of equations. Okay. And now, well, we do have a nice technique for solving linear equations. We know to use the augmented matrix method. Maybe before I rub this out, do you have any comments, Tarig?
No, that's good.
No, so yeah. I mean, it is quite wordy, but we are expecting you to try and present in a nice, readable manner. Right. And if I was doing a question like this, I probably wouldn't have done much rough work to begin with, because it is really just, there isn't that many ways to start the question. I think you need to, it asks you for the linear equations, you need to give the linear equations. So that was the answer to part A. So part B, so it really is stepping you nicely through the technique. You have to now row reduce to solve this system of linear equations. And it does say here row reduce an augmented matrix, so we are asking you to use the, yeah. So yeah, do use the augmented matrix method if you want to answer the question. This is part B. So as an augmented matrix, this is, well, let's take the information and put it into the augmented matrix. So the first linear equation I had down before was you had 10, 6, 5 totaling out to 210, 20, 16, 12, which was a total of 488, and 10, 14, 9, 3, 4, 6. So this would be easier if I still had those equations written out. Remember, the first equation was 10x, 6y, and 5z. So this is actually transposed from what the table looks like. You actually have those numbers going across instead. So make sure it's good that you get the linear equations out, also to make sure you get the right matrix here to try and solve. I did mark this exam last year. I think a lot of people tried to jump too far ahead and had this the wrong way around. All right. So we know what to do here. We want to row reduce this matrix. I still think I like circling the leading entries I want to get rid of. So I want to get rid of this 20 and this 10. I'm going to do that using this 10 here. I won't divide by 10 because that was just going to lead to fractions here that are going to confuse me. So I'm just going to do it with these numbers here. So we need to take row 2 and make it row 2 minus twice row 1. So just take off 2 lots of this equation. And at the same time, I'm going to take row 3 and just take off 1 lot of row 1 to get rid of this 10. So use this 10 to get rid of that 10. Alright, so 20 minus 20 is of course sorry. Copy down the information. So first row unchanged. Next row I'm going to take 20 minus 20, and that's a 0 because that's why I did it. And this one will be 16, and I'm getting rid of 2 6s, so that's minus 12, is a 4. And 12 minus 10 is a 2. I've got to be careful here, that's 488 minus 420, which gives me 68. You, I think, have a calculator in this exam, so feel free to do some of these on the calculator, but yeah. Alright, so let me just double check that one. So 420, another 68, yep. Here, this is much easier, just 10 minus 10, 0. 14 minus 6 is 8. 9 minus 5 is 4. And 346 minus 210, let's see, that's 90 with a 46, so 136. Right. So yeah, and again, you'll have to get these numbers right, otherwise it's going to make the rest of your calculation impossible. Or you won't be able to come to the correct conclusions if you make mistakes. So now I want to get rid of this 8. That's quite easy. I can get rid of 2 of those 4s. So it looks like I have space underneath. Let's just take row 3 and make it row 3 minus 2 lots of row 2. So use this 4 here to get rid of that 8. So the first equation didn't change. 10, 6, 5 with a 2, 10, 0, 4, 2, 68, and 8 minus 8 is 0, 4 minus 4 is 0, and 136, well if I double this I'm going to get 120 and a 16, so that's 136 as well. I get 0, 0, 0. So you can actually see that this system has, well, it probably doesn't have a unique solution. In terms of real numbers, there's definitely no unique solution. So these are our 2 leading entries. So it can be solved, but there's going to be a parameter in our solution. So the question actually says, by reducing it, show that there are infinitely many solutions. So it depends on how I want to do that here. I can actually explicitly give you the solution. Oh, actually, sorry, I should have gotten rid of that.
Oh, this thing?
Yes, sorry, that was... Sorry, I accidentally left some text on the screen which may have obscured what I was writing. Okay. Alright, so there's more than one way to argue that there are infinitely many solutions. One is to actually just give the solutions. So maybe I should just do that. So yeah, one way to do it is just to argue there is going to be a parameter in this solution. There is a non-leading column here. There are solutions because this is non-leading, but there are infinitely many because this is non-leading. But it might be clearer just to actually show that there is a parameter in the solution. So for part, this is continuing with part B. So since the augmented column is non-leading, this system Well, it has solutions. I'm not saying how many at the moment. And since the third column is also non-leading, there are infinitely many solutions. If you want to be even clearer, it is a one parameter set of solutions. Just because there is only going to be one parameter in the end based on this column here.
Josh, could one have said, since the third column is non-leading, there are infinitely many solutions, without the first sentence?
Well, I don't think that's not necessarily true for all matrices with that property. Because if this column is not non-leading...
Yeah, since the third column is non-leading, if you're in...
Well, I'm not personally happy with that, because if I was to change it to a 2, for example, then your statement still, your sentence still, you could still say the third column is non-leading, but that doesn't mean there are any solutions because this was non-leading. So personally, I wouldn't have been 100% happy with that. I may not.
Yes, that's fair.
Because it is important that this doesn't have any obstruction to there being a solution. This cannot block. If this is a leading column, there's definitely no solution. So you need to sort of. That does need to be non-leading. That is an important. If it was leading, there are problems. Mm-hmm. So I think this is an important statement to make. Okay. That being said, if you didn't make it and then just showed me there were infinitely many solutions, I can't complain either, I think. So this is actually sufficient for part B. Without solving it, this does prove there are infinitely many solutions. But since we need to actually do some solutions in part C, I think I might as well just give it to you give you the parameterized family. So let's go a little bit further than this and actually work out what these solutions look like. So we know there are infinitely many solutions with one parameter here. So let's actually just introduce that parameter. So this was z. Let's let z equal t. T is a good name for a parameter. You don't have to choose t. You could leave it as z, but I think a parameter-like name is much better. It makes it clear to those reading that you are parameterizing your solution. So let z equal t. And then, well, if you look at this equation here, it tells you that 4 times y plus 2 times, in this case, t, is equal to 68. And here's a chance to use a nice symbol. So it follows from that. So this tells me that from this line, it follows that 4y equals 68 minus 2t. So, do you teach the students see this notation?
I might have used it myself, yes.
Yeah.
But so I have a different problem. Could I not have just used the parameter z?
No, you can use the parameter z. I only do this because I think it makes it clearer for whoever's reading that it's a parameter-like name. Mm-hmm. So it's clear. I just personally, I find that clearer to say, okay, I'm using this as a parameter. Let's give it a different name to distinguish it. So that's just my own choice. If you left this as z, that's also fine. I can't complain about that. But my own personal is, I think this is clearer myself. I wouldn't mark someone down for using z, but that's not what I would do personally. So it follows then from that. So this implies that y is equal to, let's see, can 68 be divided by 4? Well, 60 can, so can 8. So that's a 15 and a 2. I get 17. Oh, actually no. Let's say it's 68 minus 2t on 4, which is 34 minus t on 2. Okay. So now I also need to solve for z. This one's going to be a little bit tricky, but not too bad. See what we get. So we have that full stop. Let me just keep up this equation I really need. This is where working on one whiteboard is a little bit hard. It's easier when you have more space. So what do we get? So this tells me that 10 times x plus 6 times, and I'm just going to slip in what y is here, 34 minus t on 2, plus 5t equals 210. And if we clean that up a little bit, well, firstly, 10x. This is nice that this is 6 divided by 2 is just 3. So 3 times 34 is 19, 12, 102. 102 minus 3t plus 5t equals 210. So I'm getting that 10x. Well, let's move that over to give me a 108 equal to 108. This becomes a plus 2, so move it over into minus 2t. Yes. And I might actually just clean that up right away into that divided by 10, which is the same as 54 minus t over 5. Oh. Hoping that's correct. So maybe if you want to check my working, there's a...
This is
So far it looks so good. So I've been doing it quite slowly because I know any slight mistake here is going to make this system impossible to solve properly. This part, yeah. So we have, we know there are infinitely many solutions, and actually I've sort of given them to you here in terms of a parameter. So what we need to do next is actually use the information that the prices were whole numbers. The prices were whole dollar values. And it says, for part C, noticing that the variables are all integers, positive integers, find all possible values for these three numbers. So we'll have to think about that. So let me just copy down what we have at the top of the board. So part C. So we have the solution, or the, let me be even more explicit. We have the parameterized solution. So we had that x was going to be equal to 54 minus t over 5. We had that y was going to be equal to 34 minus t over 2. And we also had that z was just equal to t. That was the parameter we chose. Now, first things first, we know that these all should be positive integers, positive whole numbers. So we can sort of see what that tells us about. Well, if we look at these three things, it actually gives us a little bit of information. So we know that t has to be positive. So since z has to be greater than 0, that implies t is also greater than 0 because they are the same. Yes. What do we have? So since x is actually greater than 0, well, that gives us that 54 minus t, well, t over 5. I'm just going to say this number on top had better be positive. It has to be greater than 0. And that's actually quite nice because that implies that t is less than 54. So we know that t can't go beyond 54. And likewise, since t is, no, since y was greater than 0, we immediately get that t is less than 34. So this one's kind of irrelevant because now I know it's somewhere between 0 and 34. Now, the hard part is, well, for example, this has to be a whole number. So 34 minus t has to be even. So I'm just trying to reduce the amount of things I need to look at. So since 34 minus t over 2 is a whole number, t must be even. If it's not even, this won't be a whole number. So that's an easy one to see. This one actually, I think, is much harder to see. So since 54 minus t over 5 is a whole number, well, that really means that this has to be 4 more than a multiple of 5. So I guess how am I gonna, maybe I won't try and say it that way. That way's a bit confusing. I'll just say, since that is a whole number, then 54 minus t must be a multiple of 5. So, for example, that means it should be like something like, t would have to be something like 4 or 9 or 14 or 19. Just those are the only options we have. So what does that tell us? Well, let's see what we get for t. So firstly, we know it's even and 4 more than, well, and we also have these restrictions. So I'm just going to list down what I think are the possible t. So the only possible t values are, alright, so this one tells me I should look at 4, that is making this a whole number, that's a whole number, and it doesn't go outside that range. I was thinking about 9, but 9 doesn't work because it's not an even number. So I'll just get rid of that one. Could be 14, that is even, and that does make this a whole number. Again, 19 doesn't work, so the next one is 24, even, and makes that a whole number. And, well, I was thinking about 34, but this should also not be 0. They're not going to sell things for no price. So, yeah, I'm going to say that one's not allowed. I think there were a few students who actually got this far and did include 34, and that I think was fine. Maybe they were giving them away for free, but I don't think it is a sensible choice. So you have these 3 possible values for t.
Although even the question says positive integers, but I would have given the mark for 54 as well.
Yeah, I mean, if you can make it this far, you're doing very well. I'm not going to go, well, that was silly.
Yes.
I mean, it was silly, but it's understandable.
Yes.
So I would give you a mark for 34 as well. But there really are these sensible options, I think. All right. But we also need to find x, y, and z. So let's just go back to tell us what x, y, and z are for these choices. I'll leave that information up. Yep. This, I mean, what I did here really cut down the options. You could have done a much, well, I would expect you to use the even property, but that thing with the ones where I was able to get rid of the sort of other ones much quicker was quite nice. So the possible prices were, well, you could have x equal to, let's start with the 4. Put in 4, we get 50 over 5 is 10. Y is equal, well, put in the 4, you get 30 over 2 is 15. And z is just that number, so z equals 4. Or, well, we could do 14, which gives us a 40 over 5, which is 8. A 14 gives me 20 over 2, which is 10. And z was just equal to 14. And the final sensible solution was x equals, well, put in 24, you get 30 over 5 is 6. Y equals, well, this will be 10 over 2 is 5. And the last one was z equals 24. So yeah, all whole positive numbers, and they all are possible solutions. None of these are terribly better than the other. Yeah. So that is quite a long question if you want to try and give a good solution. Do you have any comments?
One thing one could have stupidly done was to go through all the positive integers and then discount.
Yeah, I think that is fine.
That would have been fine, but very long-winded.
Yes.
So this is optimal.
Yeah, the reason I was doing this is I knew there must have been some information I could grab. It is hard. I mean, this one, I think, I would be surprised if most people get the fact that even that cuts down your search space by half. This one makes it a lot smaller because I really just got the answers immediately.
Cuts it down by a fifth, in fact. Yes.
Yes. Right.
Almost a fifth.
So you'd like to try the next question?
Yeah, I'll try. So I have a question for you, Josh. We're going to go to the seminar at 12.
Are you?
Are we?
I was not.
I see.
Do you want to?
I would like to, if possible.
Okay.
Now, I'm sorry, I might have to run in 15 minutes. But do you want me to do the Markov question, or do you want me to do a calculus question?
maybe a calculus question because you were lecturing calculus.
I wasn't.
You weren't? Oh, sorry.
I'm happy to do I'm happy to do it anyways.
Okay. Well, whichever one you feel the most comfortable with.
Okay, I'm most comfortable with the Markov question, but maybe being comfortable is not a good thing. Anyhow, let's see. Okay, we move on to the second part of question 1. Are you sure you don't want to go to Norman's seminar?
Well, Norman is recording the seminar,
Ah,
and I've already set up the camera for him.
I see. That in fact could be an option. Let me do. Okay. Cool. Is it now on or not yet?
That's all.
No, the question.
Yeah. Oh, okay, yes. I'll get into position.
Okay. Cool. So the question is about Australian families living in 3 different areas, and it gives us the probabilities of a family moving from one area to the other in the question. Again, so this is a Markov process question, and the first part of the question asks us to write down what the transition matrix is for this Markov process. So let's go. So this is question 1, part 2.
There's a bigger version here.
Yeah, oh, brilliant. Okay, sounds good. So the probabilities are written up in the question, so we just need to sort of translate them to the transition matrix. So the way I would do this is I would say the transition. I think with these presentation marks, it's better to be safe than sorry. So if you happen to have time, write more as opposed to less. But that's it. Anyhow, the transition matrix. This Markov process is and then you say T is equal to. So if we're going to have urban, what's the other one? Suburban and rural. And here urban, suburban, and rural. So the probability that goes on this thing is the probability from going from urban to urban. And so from urban to urban is hence the probability of staying is 0.6, and the probability from going from urban, let's see, how do I do this? I put on there. Just let me try and remember what goes on. So this gives me the probability of moving from urban to something else. So this is okay. I need to remember which one it is, the transpose or the matrix itself. But let me get rid of this. Where's my keyboard rubber?
Did I steal that? Yes, I did. Yeah, I was going to ask, would you put the to and from label on this?
I wouldn't put the to and from label, but do you want to?
I don't know. I think that was being happening in lectures, wasn't it?
Yeah, I think that the typical solutions don't seem to have that.
Okay.
I don't know. Do check. So this times this is going to give me the probability of moving from urban. So yes,
these ones do.
Ah, okay.
It's not necessary, but it does.
So
I think at this level, it makes it quite clear.
Brilliant. So let's put a to and from labels. I'll put them in colors. I'm getting strange deja vu, but anyhow. So let me write them down to be careful. This is from the other way around, isn't it, Josh?
Yes, it is the other way around.
Yeah, the way I remember this is I multiply it by the column matrix 1, 0, 0, so that tells me the basically second part of the question. It tells me that what is the probability of somebody moving from urban to something else.
Yeah.
And then I can read that off. And basically, it's the first column.
Yeah.
So
I like to think of it as old information coming in and new information going out. So that's my way of thinking of it.
brilliant. So I'll fill in the rest of them just by reading what the question is. The probability of suburban family moving to a rural region is 0.2. Suburban family to rural is 0.2. Probability of a suburban family moving to an urban region is again 0.2. And hence the probability of a suburban family staying in suburbia is 0.6, because the sum of the elements in a column has to be 1. And now we have the last bit of the matrix. The probability of a rural family moving to a suburban area is 0.7. Suburban. Probability of a family staying in a rural area is 0.2, which means that this is 0.1 because these here have to add up to 1. I think that's okay. Good. So that's sufficient for part A. So let me look at that properly. So that's part A. And now let's think about part B. So this is the transition matrix after a decade. So here the time step T is a decade. And we're asked to find what is the probability of that a family will live in an urban region 20 years, which is 2 time units after the fact. So I have a family that's living in a rural region. What is the probability of that family moving to an urban region after 20 years? Since the time step is a decade or 10 years time. This is given by T squared times the matrix 0, 0, 1. Why is it 0, 0, 1? Well, it's 0, 0, 1 because my family starts off rural. Okay. So it starts off rural, so it lives in the rural area with probability 1. Okay, so I'll rub this off and then carry on there. I might need this transition matrix, but let me write it here before moving on. Do you have a comment, Josh?
No. I will say, with this particular exam, when we designed it, we were very explicit. It does say 2 time units, 2 decades, for the 2 decades. We weren't quite brave enough to just leave it as 20 years, because I was slightly worried people might try and do a high power.
Yeah, I would have done 20. I would have made that mistake if nobody.
Yeah, so we were trying to be not too nasty when designing these questions. One thing I might have done differently is Tarig did explain on the camera what this meant. I might have actually had that information written down, saying what this actually meant. So that's a change I would have made. Maybe just have explain where this 0, 0, 1 comes from.
You could say where.
Okay.
Well,
I guess, what do we call it? Where
the vector 0.
where So what is it? 001 is. Do you call them the state vectors?
I don't know. I didn't use that term. No.
So.
Is the initial?
Yeah.
Maybe.
Is. I'll just say why it's used. It's used because the family starts in a rural region. So I guess, yeah, if you sort of wrote this down and went, ooh, I should have explained that, just add a small explanation about why it was used.
Brilliant. Cool. So I'll rub this and carry on, even though, yeah, put this here. Cool. Now, okay, we've got that. Then, i.e., the probability vector we seek is what was it now? 0.6, 0.2, 0.2, and 0.7, 0.2, 0.1, 0.2, 0.2 and 0.6. Is this right?
Yep, that's right.
Squared times 0.01. And this is equal to, I'm going to first multiply, okay, I'll just do it like this, I'll tell you later what I've done. Times so here I've multiplied the matrix by this vector. Remember, matrix multiplication is associative, so I can first multiply the last two bits and then multiply the first one, which makes it easy. And then now I need to do this calculation. And this is, it's not, okay, you guys have a calculator, I think, in the exam, so you should be able to sort of compute this, but I can't be able to. Give me the solutions, yes. Thank you. So it ends up, the solutions end up looking like this. 0.22, 0.58, I said 8, 0.2. Thank you. Therefore, the probability distribution of the rural family. Correct me if a rural family after 20 years of the rural family's location, maybe. Rural family's location after 20 years elapse is 0.222, where this is urban, this is suburban, this is rural. Therefore, and hence, the probability of the family living in an urban area is 0.22.
Right. Yeah. So I mean, yeah, that's exactly what they want. I feel like you might have repeated yourself with this because
A little bit,
I think you sort of meant it kind of went off the page here, but you said after 20 years is this is the probability vector. I guess technically to make everyone happy, put a full stop. And yeah, I think this might have been just repeating what we already just found here. So I would have been happy if from here it was straight to the conclusion. Here's what the information tells me.
Yeah. So this is me being better safe than sorry.
Yes. I probably, yeah, this isn't going to cost marks, but it does sort of...
It does cost time.
Cost time,
Yes.
And just to answer the question, yes, calculators are allowed, but they have to have the UNSW approved sticker. So if you don't have the sticker yet, make sure you get down to one of the student centers to get that UNSW approved sticker. I think any of these student centers can pretty much do that for you. So did you want to go to Norman's seminar? It's...
I did, but I could do the second part of the question and run away. And join that halfway through.
That was...
No, the what is it? The best line of best fit.
Ah, I see. Well, I mean, it's 12 o'clock exactly now, so if you want to go, now's the time to leave.
I feel like I'm sort of leaving in the deep end here. I really didn't do too much.
That's fine. I'm just going to go for another hour, then I'll stop.
Okay.
So, if you really want to see the seminar, that's fine.
Okay.
Alright.
But I don't know how if I should announce this. We're probably going to go to lunch with Norman after the seminar, so if you can join us as well.
Okay. That's good to know. Alright, so I'll continue on for one more hour by myself. So yeah, unfortunately someone being sick does make this a little bit hard. Let me just set up the information here.
Sorry. I feel so bad for leaving.
At least I got some help. Thanks.
I feel like I should have. I didn't know the first question would take that long.
I did not know that either.
I felt that maybe I should have done the first two questions and then. I thought. Anyway.
Anyway, we're still streaming, so.
I'll just put. I know. I'll put this out.
Oh yes, thank you. Let's see. So, sorry for those of you watching, I need to get these in the right location. Okay, so this is a fairly common thing to be in one of our exams. We are trying to also teach you how to do some coding with the mathematics. So you have been learning during the session on how to use Maple. So you will possibly see Maple output in the exam. And this is nice for you because it actually does, it's really, the calculations are all done for you. You don't need to do any calculations. But you will have to explain why the calculations were done or how the calculations are helping you find your answer. So for this question, it shouldn't really take too long because although there are a fair number of data points, all the calculations have been done already. So there are a lot of parts to this question. Okay. Right. The least squares line of best fit. So maybe I'll just remind myself of how we find the least squares like this did. So this is part 3. So you've learned through the session that the line of best fit y equals mx plus b is given by, well, it's given by the solutions to A transpose A times M B is equal to, let me just check what the code was doing. Well, I'm just going to say equal to B, where A and B are the matrices defined in the text. All right. So, yeah, I think you've maybe learned by saying that you set up your data, your observation, these are your points of observation and these are your actual observed values, and then you multiply by the transpose to get this. This is usually written as A transpose times a vector, the vector of the data. So the x, why or x? Well, it depends on the notation. But yeah, if you look at the notation they've given here, this is really the transpose of A times the observed values. All right. So what we want to do, so let's use the maple output. So using the maple output, this is, and I don't want to use all these decimal places given here. I just want to do a small, I just want to use approximately these values. So I'm going to say 2, 3 decimal places. We have the following equations. So we have, it's really the equation to 3 decimal places, 8.223. Actually, I only use 2 decimal places. So I'll say 2 decimal places in my solutions. So 8.22, 5.09. You could do it to 1 decimal place, but I think this might be a reasonable compromise. And that has to be equal to, again, I'm only going to round to 2 decimal, say 2 decimal places. 31.15, and 25.19. Right, so I want to get these, I want to find out what values of these 2 numbers will solve this equation here. Now, very nicely, we know how to solve equations like this. We can just use the inverse matrix. If I multiply by the inverse matrix, it'll give me these parameters. It'll give me the parameters I'm looking for. Yeah. So here I would explain. I'm trying to explain where this information is coming from. We sort of have a technique for finding it, and that gives us this. And the maple calculation did all these Maple did all the calculations for me, so I don't need to do any more. Now, I think that's actually all the information I can get from Maple, so I'm going to that Maple output. Let me just hide that to save space. All right, so let's solve this. Let's actually just multiply by the inverse. So it follows from this that the parameters we want, m and b, will just be given by multiplying by the inverse matrix, which I'm not going to calculate just yet. I'm just going to say I want the inverse. And all right. Okay. So, well, depending on how you remember it, I like to remember the inverse matrix. Firstly, let's get that determinant down. So this times this minus that times that. Thankfully, I did the calculations last year and left myself some solutions. So that is going to be the determinant of this matrix, and I think this is exactly the determinant of this approximation. So, all right. And, well, so the technique I remember is these two have to switch. So you switch the things on the diagonal, and then these two actually get to stay where they are. I don't move these two, and I wouldn't even notice if I did, because in this case they're the same. But a penalty for staying where it is it has to get a minus sign. So that's not a mathematical way of, that's not really mathematics, but it is a nice mnemonic. It's a nice memory device, remembering how to change this to get the right answer. And I am going to multiply that by 31.15 and 25.19. Now, if you plug this into your calculators, this isn't going to be a nice number when you do the calculation. It'll be 6 times that minus 5 times that divided by this. I doubt you're going to get a nice number, so I'm just going to truncate the approximation, get that, well, approximately to 2 decimal places. I got 2.49 and 2.08. And that will allow us to answer the first question, because these were the parameters we wanted. I said it was mx plus b. Ooh. I just realized I did make a mistake. I did use the wrong notation at the start. Because I used lowercase x and lowercase y. So that would have been, I would not give myself full marks for that, saying that. At the start I said, I was trying to solve y equals mx plus b. That was wrong, because I was actually looking for a least squares solution to y equals m capital X plus b. And these are very different equations. So yeah, I would not give myself full marks for doing that. I would knock a mark off for not paying attention to what it is I'm truly doing. So what I should have been talking about was we're trying to find linear solutions to that. If you actually take this data and plot it out, it does actually look pretty linear in the log values. All right. So yeah. But this allows us to give the least squares line a best fit. Thus, the least squares line of best fit is, and really I've made approximations on the way, so this isn't the perfect solution, but for these sort of things an approximation is a good enough solution. So the approximation is y equal to, so my line of best fit I'm going to use is, well, let's round this to just one decimal place times x, and round this to one decimal place to get plus 2.1, and I believe that is the answer we wanted. And I'll just explain what happened to those numbers, rounding m and b to one decimal place. Just to explain why didn't I use these numbers? Well, I mean, these are an approximation already, so if I just drop a bit of, I'm not really getting a worse approximation just by taking one decimal place instead of two. So maybe I should say here I already said 2 decimal places. 2 dp, I think usually we can understand you mean decimal place. Okay. Now, see, there's some comments popping up. Yushin, are you taking a break? No. No, I think we should probably try and get through as many as possible, and when we hit 2 hours, just stop. I just want you to see sufficiently many examples of what I consider to be good presentation. So, starting off with words, I don't start off with just the symbol. If I just started off with this, well, I think linking words at least make it more legible, makes it easier for people to follow what you're doing. You're saying, thus we have this. I could do a bit more explanation here, but I did not, and that gives me this. And it follows, so this isn't the best because I'm using thus and thus quite a lot. It's just, well, yeah, not great, but it's not, yeah. I think it could be presented a little bit better. Now, we want to actually use this information because this was a least squares line of best fit for these log values, and they're actually very unusual log values. They have we're taking the log of a shift, and so we want to take this least squares line of best fit and try and get back to some sort of equation about x and y, the original x and y values. What I would really love is I would love an equation which would predict an x value given a y value. So I'd love to see something of the form y is equal to so on. So that way I just plug in my x value and it gives me a prediction about what the y value should be. So the question just says, hence find y in terms of x, lowercase y in terms of x. So let's just take this information and put it back into lowercase y in terms of x. So for part B, the least squares best fit in x and y, so capital X and Y gives, well, it gives the following approximation, that the log of lowercase y minus 3 is going to be equal to 2.5 times the log of lowercase x minus 5.5 plus 2.1. That's what it says here, plus 2.1. So this gives us a way to relate lowercase x and lowercase y. But I would like to see y just being a function of x. So the easiest way to do that is just to exponentiate both sides. So exponentiating both sides gives, well, it gives me that y minus 3 is equal to, well, in this case, the exponential of 2.5 log of x minus 5.5 plus 2.1. Now, to simplify this, I'm going to have to, well, the exponential of a product is the product of the exponentials. So I get an exponential of, well, also I can use my log law to pull this in up here. So this is 2.5 up here. So it's the exponential of log of x minus 5.5 to the 2.5, and that's multiplied by the exponential of 2.1. Now this one simplifies quite nicely because the exponential of a log just vanishes. It's just the inverse of each other. So this is just going to be x minus 5.5 to the 2.5, and I probably need a calculator to work out what is the exponential of 2.1. So according to this, I'm just going to do an approximation, because again, these numbers were found by, these 2.5 and this 2.1 were found by approximating. So I'm just going to say that this is approximately e to the 2.1 is just 8.2. And let me just add a reason for where that 8.2 came from. So where 8.2 is approximately the exponential of 2.1. Just to explain, anyone who looks at what I did, why I got rid of my e to the 2.1 and replaced it with 8.2. It's because they are approximately the same number, just to one decimal place. All right. So that's not quite the full answer, because this is y minus 3 is approximately that. But let's just rearrange that so we get a hence y is approximately 3 plus 8.2 times x minus 5.5 to the 2.5. And that's my, so this is a nice equation. It tells me if you give me an x value, I can give you a prediction for what kind of y value you should expect when you do your measurements. And that's what these are doing. They want to give you predictions. You want to get some sort of, the data is telling you, it approximately looks like this relation here. Okay. Now part C, I see some more comments. So there's a question about whether we should be putting equations separately on new lines. I think I would. Well, I mean, this one I would. It's a very long equation just to have sitting on it if I want to put it in the text, but you could also just have it part of the sentence. That is fine. Although being displayed like this does draw your eye to it. I think this is an important equation, so the best fit gives us this. I want you to see this equation. It's a very important equation. I'm putting it on its own line centered. Long calculations like this, I also tend to center them and try and line up the equal signs. I don't like this because I didn't line them up, but again, in an exam, I'm not going to be too picky about alignment. It could look nicer, but it's fine. And yeah, so the big equations, the important equations, I do center them and put them on their own line. If there's a very short equation, like this one here, I said where this is approximately this is part of the text. But these are small issues, I think. As long as I can read through what you're writing, or whoever's marking can read through what you're writing and it flows nicely, I think that's good presentation. It should sort of sound like a nice argument to hear. So yeah, don't worry so much about where you're putting the equations, just as long as the argument is sort of flows nicely. So here I gave this, and then I have to exponentiate both sides, giving this, and just a small explanation for anyone who was confused about what happened between these two lines. And my conclusion. My conclusion is that we have that this y, the y's are approximately given by this. Now part C is actually, let's use our equation to predict to one decimal place what happens for an x value. So yeah, we want to find out what happens at x equals 7.5. So somewhere between the two values given in the table. So you have 7 and 8. So when you get your answer, you should be able to go back and look, does it actually make sense? Does it actually match what the data was telling me before? Because if it's quite nonsensical, then maybe you've made a mistake and maybe you want to fix it. Maybe. Right. So for this question, I think I did have to use the calculator quite a lot when I was working through. There were certain points where I had to do the calculation, and then I didn't want to put in, and then I was just rounding them to 2 decimal places most of the time. That does introduce spam. Alright, so that was part B. Part C is, let's actually give it a go. So let's see what it tells me about x equals 7.5. So at x equals 7.5, our relation, so the one we found in part B, actually let's say that, our relation from part B predicts, so we get y should be equal to 3 plus 8.2, or maybe approximately equal. I'll just say equal to for here. It's not. So I mean, this is exactly what it predicts. So this is equal to the prediction at least. And this is 7.5 minus 5.5, which is just 2, and that's to the power of 2.5. Now, when you plug this into your calculator, at least when I did it, I got approximately 49.4, and I'm only going to 1 decimal place. Because again, there's so many approximations through here, I don't want to carry too many decimal places with me. And so that's saying it's about 50. And if you look at the values on the table, so it went from 25 to 80, it is at least between those numbers, so that does kind of seem reasonable. So I actually would add that to my conclusion, that so which seems reasonable compared to the values in the table. Just to maybe, I mean, if this was a report I was writing for someone, I might want to draw their attention to the fact that this is a good prediction based on what we already saw, that it does nicely fall between those values we're finding. So the model's not terrible. So yeah, so that's what I would do for this question. I don't see any more comments at the moment, so I might move on. Let's see. This next question. So I will show you this next question, but I may not answer it. Now, this was the hardest question in the last exam. And we put it in there because we really wanted to see if anyone could do it. But nobody could. So, for that reason, actually, I don't want to discuss the answer because I would like to leave it as a challenge. I would like to, if you want to try and answer a question that nobody last year could answer, give this one a go. It is quite tricky. I think even students who are doing our 1231 course still would probably find this question very tricky. So it is in the last year's exam. If you want to go have a look at it, you can go have a look at it, but I'm actually not going to answer it. If you want to come to my consultation times and have a discussion about it, I'll give you some hints, but I won't tell you what to do. It was only worth 2 marks. So yeah, it wasn't a So, I mean, that question was only worth 2 marks. So we made it worth not too much because we knew a lot of people may find it hard. So what about this next question? This next question was worth 3 marks. So we just have, it's a very kind of simple question about calculus. You have a rupture in an oil tanker, and you're given an equation someone's come up with. Someone's given you this equation, and it's supposed to model how the concentration in the oil varies with distance and time. Now, there are very unusual units being used here. Alpha is the unit of distance in kilometers, which is not what I would have chosen for distance, but and beta is the time in days. And it says here that 9 days after the accident, a monitoring station is set up 12 kilometers from the boat. So it's got only 2 questions here. Find the concentration of the surface oil. So at the point of the station, find the concentration of the surface oil and how the rate of change of oil concentration, how it changes with respect to time. So I don't think there's too much to say about this question, just to make sure you sort of explain what's going on. So this is actually the question 2, part I. So let's just translate what the question's saying. So 12 kilometers from the boat well, alpha is measured in kilometers, so it means alpha is equal to 12, and 9 days after the incident means beta is equal to 9. So it's a little bit too simple here. They gave you the information in kilometers, and this is measured in kilometers. It would be a more interesting question if this were different units. Beta was measured in days, so this is 9 days. So yeah, the units do match up. Be careful. I don't guarantee that will happen with this exam. I didn't write this exam, and it could happen that the units are not the same. The units in the question and the units of the units of these variables may not be the same. So yeah, for this part of the question, we can just use the formula. So using the provided formula, the concentration at this point and time is Well, what is it? It's just given by C equals to, so the formula says 720 over alpha, which is 12, and the square root of beta, which is 9. So that is 720 over 12 times 3, which is 720 over 36. And this question was set up to have a nice answer. That is exactly 20. Now, if you said is equal to 20, I'm not happy with that because there was units with this number. So this is liters of oil per square kilometer. So I'd say this is, the units are liters per kilometer squared. Some sort of thing to indicate what this number means. 20 by itself, it has units. You should put the units down, I think. And that's especially going to be true in the following question, where you have to work out the rate of change. All right. So yeah, I would knock a Markov for not using units here. This number, the 20 has something associated with it. Units are very important. All right, so what is the rate of change with respect to time? So I'll just drop this out. Right, so the rate of change in the concentration is given by, well, it's given by just looking at what the, and this is a two variable function, so it should be a partial derivative because there are two variables in the question. So the partial derivative of concentration with respect to time. And it's a quite easy calculation to get at. This is minus a half beta to the minus 3/2 times by 720 over alpha. And this does have units, but I won't add them just here. I'll add them when I actually calculate the number. So again, at the time and location described in part A, we have that the rate of change of the concentration with respect to time is going to be minus 1/2 9 to the minus 3/2. So this is actually going to be, well, that can be, I'll write it down in a second, times 720 over 12. And, well, I guess there's no shame in pulling out a calculator. You could probably get this one almost exactly by hand. This number's not too hard to work out. But if I use the calculator, I got minus 1.11. And again, that number sort of doesn't mean anything to me until you give it units. So this is liters per kilometer squared per day. So the concentration drops by, well, roughly, as an approximation, it kind of drops by this much per day at 9 days. So, yeah, again, units I think are important to make sense of what the size of this number really is. All right, and that's all I would really write for that question. It's only a 3-mark question. But yeah, So it shouldn't take too long to get through the calculations. You just need to make sure you're sort of writing down, explain what you're doing with words. And again, like Tarig said before, the more words, it's better to sort of write more than less. But again, don't try and write too much. If you repeat yourself again and again, you're wasting time, and that might just be costing you the opportunity of working on other questions. All right. So what's next? Actually, there are only 2 more questions left, I think, so I might as well just go over. Yeah, I might as well go over both these questions. Right, so this is a question about an integral. Well, at least it is about an integral, but it may not explicitly say it yet. So you're told that the growth rate of a tree, given in meters per year, has a very particular form. So what makes this question tricky, I think, is this integral does look more complicated than it really is. So first part is, well, show that this model predicts positive growth rate for the time provided. All right. So if you're looking at the equation there, let me just. If you had a question, I just want to double check what I said. So yeah, someone was asking, was I going to put up solutions to the matrix question? No, again, I think if nobody could get it, I would like to leave it as a challenge. I actually think it's not too hard if you are someone who's determined to solve the problem. You can solve the problem if you give it a go, but a lot of people wanted an easy way out, so they gave up on the problem. So I think I should leave it as a challenge. If you can get it done, you should feel proud of yourself. So the first part here is we're told to show that the growth rate is positive for this time period, because it's actually not going to be, this equation won't always return positive numbers. So probably the easiest way to see this is to note the following. Note that if t is between 1 and the exponential of pi over 2, then, well, actually, the log is a very nice function. So if I take the log of t, it's still going to be less than the log of e pi over 2, and it's going to be greater than the log of 1. And I might give a reason. This is since log is strictly increasing. It's what we call a monotonic function. It only goes in one direction. In this case, the log function is strictly increasing. So things that came later, log says they're later as well. So I'm getting that these are between these two values. Now, actually, these values I can easily work out. That tell me that the log of 1 I know to be 0. So 0, the log of t is between 0 and pi over 2. So that's helpful because if I'm looking, what's really troubling me in this equation is that cosine term. Because log, well, as long as t is greater than 1, log will be positive. That's what I just said here. Log will be positive or non-negative. Now what I really need to worry about is whether that cosine term is going to be 0. So it's not a trouble, because if you look at the cosine term, and since cos is non-negative over, well, it only returns 0 or greater over the range 0 to pi over 2. So the cosine function, when you put in numbers from 0 to pi over 2, you always get positive numbers. So since cos is non-negative over that range, we have, well, I'm going to have that the cosine of the log of t is greater than or equal to 0 for the log of t between pi on 2 and 0. So the log term is positive and the cosine term is positive. These are the only things that, the last term there was a t, and t is always positive. Hence, well, let's just say hence. So what do we have? We have that the cosine term will be strictly greater than 0. Sorry, not strictly greater than 0. Cosine term will be greater than or equal to 0. The log term will be greater than or equal to 0. So this is definitely greater than or equal to 0. And therefore, well, you have to have that r of t is greater than or equal to 0 for t between 1 and the exponential. So yeah, it's, maybe I'm a bit wordy here, but I really need to worry about, is this log term going to be positive, and is this cosine term going to be positive? So whatever you write as your solution, that's what I'm looking for. I'm looking for, you have to explain to me why log is positive and why cosine is also positive, because they won't always be positive. It's really this restriction is important. Now, it says to use an appropriate integral, find how much growth there was from time equals 1 to time equals e to the pi on 2. Yeah. So you can do this part without having, these two parts are independent. So part B doesn't really rely on part A. You could do them separately. No information from part A is needed. So this is a tricky integral. So I would probably do it by substitution. The total amount of growth over this period is, well, you are actually just going to integrate the rate of change. So it's going to be the integral from 1 to the exponential pi over 2 of r of t dt, which is the integral from 1 e to the pi over 2 of the cosine of the log of t times the log of t over t dt. So that's a good start, knowing what integral we need to do. But this is quite a tricky integral. So first thing I'm going to do is I'm going to make my life easier by doing a substitution. If I do the substitution u equals log t, it's a little bit easier. So setting u equals log t, which gives me that du is equal to 1 over t dt. That's my change in the volume element. What does the integral become? So setting that the integral becomes, well, it becomes the integral. I'll work out the limits in a second. It's the cosine of u times u du. And the limits, well, we already know, well, yeah, t is equal to 1 gives the log of t is equal to 0. That's kind of what we saw in part A. And t equal to e to the pi over 2, the upper limit is just going to become pi over 2. So that's the total growth. Now this is much nicer because I can almost integrate this, but I need to use integration by parts. So maybe I shouldn't have used the notation u, because I usually use u and v for integration by parts. I might actually make that change. If I'd been thinking about what was coming up, a different substitution would be more natural. So just to make the notation more standard, let's make, sorry, that was right. Let's make x equal to the log of t, which gives me that dx is 1 over t dt. So this is actually just cos of x times x dx. All right. So there is really no way out of doing this, rather than just, you really have to do integration by parts. So I'll do that the way I usually see it. So let's let me just be explicit. To do integration by parts, let's let u equal, well, I want to take the derivative of x, so let's let that equal x, and dv equals the cosine. That gives me that du is equal to 1, and v, well, if I integrate cos, I get just sine, which is fairly nice. So this is nice. I'm going to transfer from x times cos to 1 times sine, and 1 times sine I'm very, very happy with. Right. All right. So to do integration by parts, we've made this choice. Hence the integral is now, well, it's now the integral. Well, okay. Let's just write it down again. So I had the integral from 0 to pi over 2 x times cos x dx, and that has become, well, the first thing you do is you multiply these two together, u times v. So it becomes x times the sine of x from x equals 0 to x equals pi over 2. And integration by parts says minus the integral of this product. So minus the integral from 0 to pi over 2 of just 1 times sine x. So sine x dx. Alright, now this first one we can just plug in the limits and see what happens. So the upper limit is going to give me pi on 2 times 1. Just pi on 2 times 1. The lower limit, well, it's 0 times also 0, so nothing. And this integral is not too hard to do. It's minus the integral. And I do need to be careful here because I commonly make a mistake integrating trig functions. If I'm feeling a bit tired, I might think it's cos, but the derivative of cos is minus sine, and I don't have a minus there. So this integral has a minus. The derivative of minus cos is sine. So personally, I always find derivatives much easier. My brain naturally can do derivatives just based on experience. The integrals, I always try to turn them around, double check using derivatives that I get what I want. So yeah, derivative of minus cos is sine, that's good. And I can plug that in, well, cos, let's see, that's pi on 2 minus, well, the upper limit gives me, a cos of pi on 2 is 0, so it gives me a 0, minus, well, it's going to become minus minus, so plus the cosine of 0. So this is just pi on 2 minus 1. Now, remember, at the beginning I said you should write your conclusions. So this isn't the end of the question. You have found the important number, but this number means something in the context of the question. So hence, and actually I might add something here. This number, well, without a calculator, pi is approximately 3.14. Divide that by 2, I get 1.57. So this is approximately 1.57 minus 1, which is equal to 0.57. So it's a positive number, like I expect. So hence the tree grew about, just because it is an approximation, 0.57 meters over this period. Of course, this isn't a sensible model of tree growth, I don't think, but it is an integral you could do, and that's really the reason for doing it. So yeah, this is approximately 0.57 meters of growth, according to this model. Alright, so there's one more question. This was a big mark question. Alright, so someone had a good question. Through these questions I've kind of been making a lot of approximations. Like here, it doesn't actually say how many decimal places to give your answer to. It says just use an appropriate integral to calculate this growth. So in some sense this number is fine, but I don't like this as an answer to the question. because it's very hard for anyone to understand exactly what that number is. If you give me this number, I go, okay, I mean, numerically it's a perfect answer, but I don't really know what it is as a number. A 0.57 or 0 point something else, I only did 57 because in my head, 3.14 is what I naturally think of when I think of pi. You want to go 3.14159 to whatever, you can do that. But again, that might also be wrong, because if you give too many points of accuracy, you're making your answer sound unreasonably accurate. So I think go with what you feel is appropriate. Usually, for myself, 2 or 3 decimal places or 2 or 3 significant figures is what I would try to do. Just, if I start going, like if I said 5, 7, blah, 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 that's a huge number. It's distracting me from the answer, which is like 0.6, that's also not bad. But if you start putting on too many digits, then you're just distracting them from the sort of what the value is. But no, there was no guideline about how many decimal places to use. Use whatever you think is appropriate. I just try to use something that conveys the scale of the number without being too large. I guess other things you might think about is, for example, the question I had with the line of best fit. There were so many approximations going on, I wasn't going to trust my answer past a few decimal places anyway, or a few significant figures. So in that question, yeah, with all the approximations happening, I was only taking a very low sort of, I was only taking a very a few digits from the answers I was getting, because I wasn't going to trust the other ones to be accurate. So the last part of the text. All right, so for the 105, one more question. So this last question was quite interesting. It's worth 8 marks, or it was worth 8 marks last year. And it had a very wide variety of answers. It's because the first part was actually, we give you this differential equation, and what we want you to do is justify it. And justifying it was quite hard, I think. Trying to find a good reason for why it was the correct equation to model this. So there are a lot of words in the first part. You have a kitchen, which is, let's see. So there's a burnt piece of toast which is leaking smoke into the air at 0.5 milligrams per second. And then there's an air conditioning unit, and you're told it removes 5 cubic meters per minute. So the first thing to do was explain why the level of smoke in milligrams per... Yeah, so the smoke is measured in amount of smoke in the room in milligrams. So it's just in milligrams, the absolute amount of smoke in the room. All right. Okay. Yeah, so the first part is really an absolute part. So letting S be the amount of smoke in milligrams, we see that 0.05, which is just another way of writing 1 over 20 milligrams of smoke are flowing into the room. I'll say flowing into the room. Now the next part's quite hard, because we have 5 cubic meters are being removed per minute. Let's see. So let's see, now here's where it's kind of important that you sort of pay attention to the units. Since the density of the smoke is, well, it's going to be whatever the absolute amount of smoke in the room is, divided by the size of the room. So it's a 50 cubic meter room. So this is milligrams per liter, I believe. 50 cubic meter. Yeah. So this is milligrams per meter cubed, actually. It's 50 cubic meters. So this is the density. So since the smoke is of this density and the air is being drawn out at a rate of, alright, so we're told, and here's where I've got to be very careful to make sure my letters look good. This is an S, and it's being drawn out at a rate of 5 meters cubed per, and I believe it's minute. There's a mistake here I didn't catch. So it's second. So it's 0.5. Yeah, so it's milligrams per second of smoke. So it's important, this actually does have the units milligrams per second. And this is being drawn out at a rate of 5 meters cubed per minute, which is the same as 5 over 60 meters cubed per second. Because really we're working in seconds. Alright. So 5 over 60 is just the same as 1 over 30 meters cubed per second. Okay. So I think this may be one of the places where people got caught, that these units are not the same. And I think I did mention that before, you have to pay attention to your units. So this is really 1 over 30 meters cubed per second. That's only one, well, whatever number that is, 0.033, whatever. Okay, so this is the density of the smoke, and this is how much smoke is being removed per second. So overall, so hence the amount of smoke being removed is, well, it's the product of these two. So the density times the rate of flow. So that's S over 600. And let's just see what the units are now. This is milligrams per meter cubed times meter cubed per second. So we get milligrams per second. So that's an S over 600. Right, so that's how much is flowing in, and this is how much is flowing out. Right. So, thus, well, the rate of change of smoke with respect to time is, well, it's really the amount flowing in, so the inflow minus the outflow, both measured in milligrams per second. And the first one we said was 1 over 20. minus the second one, which was s over, it's really an s, over 600. And I might give this the units just to remind myself, milligrams per second. So I think that's a good explanation of where this model came from. Now, even if you can't explain where the model comes from, you should be able to apply the model. So we have to solve this differential equation with an appropriate initial condition. So we didn't tell you what the initial condition was, but it should be clear from the text what the initial condition should be. That's why this question is worth so many marks, because there are so many parts of the question which just aren't told to you and you need to pick up from the text. So it says here that the kitchen is initially clean. So since the kitchen was, well, I'll say smoke-free, the smoke-free kitchen, since the kitchen was smoke-free initially, let's take that S is equal to 0 at T is equal to 0. So no smoke at the initial time. So we have to now solve this. And well, okay, actually this is part B. Let me remind myself what I did last time. Yeah, so this is a linear equation, and it's a linear first order equation, so probably the easiest way to solve this one is to use an integrating factor. So the equation can be written as the following. So we have that ds dt plus s over 600 is equal to 1 over 20. And this is a simple equation which we should already know how to solve. So let's just say how we solve it. So this has integrating factor e to the integral of 1 over 600 dt, which is just e to the 1 over 600 t, or maybe I'll write it this way, e to the t over 600. Right. So there's a question in the chat. Someone's asking, is it 1 over 12 instead of 1 over 30? Now, let's see, where did the 1 over 30 come here? You seem to be correct. What did I do wrong? So yeah, I wasn't paying attention. The air is being cycled out at 1 over 12 meters cubed per second. So that was a mistake I made. That the air conditioner, so if you imagine the air conditioner sucking the air out, it was 1 over 12 meters cubed per second. This is one of the reasons we actually gave you the equation to begin with, because there was a high chance, like me, you may have made a mistake if you didn't know the answer. But this is the correct equation to deal with. So we gave you the equation because we would like you to try and solve this equation. And we would like you to give a good explanation as to where it comes from. All right, so this is the integrating factor. And at least when I was teaching this course, I like to point out that you know what the integrating factor does. So you can usually shorten your explanation just a bit by saying multiplying by the integrating factor gives, and the whole reason we multiply by the integrating factor is it turns the left-hand side into a nice derivative, just the derivative of this times the integrating factor. So that's what happens when you multiply the left-hand side. You can verify it by taking the derivative, but you should know that when you multiply, that's what you get. And on the other side, we get e to the t over 600 over 20. Now this is nice because I can integrate this. This is just, I'm just going to get rid of the derivative. And this one, it's not too hard to integrate. So let's just integrate both sides and say that this implies that s times the exponential of t over 600 is going to be equal to, well, when I take, well, let's just double check. So if I integrate, I'm going to get a 600 coming out on top. So I'm going to get 600 over 20 e to the t over 600. And 600 over 20, well, that's 60 over 2 is 30. So I'm getting a 30, ooh, not quite right. I'm going very, very bad. When you integrate, there's always a constant of integration. So that is 30 e to the t over 600 plus c. And I can just double check this does do what I want. When I take the derivative here, I divide this by 600. 600 divided by 30 is just 20. Yep. So I think this is correct. And resist the urge to look at my worked solution. All right. Now here's probably a good time to apply the initial condition. Because this is true for any solution. This is just a general solution, but I'm really only interested in the solution where s is equal to 0 and t is equal to 0. So using s equals 0 at t equals 0 gives, well, let's just plug it in and get that this is 0 has to equal, well, this is 30 times e to the 0, so it's 30 plus c. So this implies that that constant I didn't know is actually minus 30. So that's the solution. That's how the smoke is increasing with time. Hence the level of smoke, well, let's say amount of smoke. Level is kind of maybe not the right word. Is s of t equal to Right, well, I need to divide by this to get 30. So divide this by the exponential, it goes to 0, minus 30 e to the minus t over 600. And that's just rearranging that equation up here with minus 30 there. All right. Now the next part of this question is interesting. So the next part says, what is the level of pollution after 30 seconds? Let's just make a prediction based on the equation. So plug the number in and get a number out. So we have the equation for the level of smoke there. In fact, it might even be better to remind myself what the units are. Yeah. So the level of smoke here is really measured in milligrams. Alright, so the next part is just plug in S, look at the time at time equals 40 seconds. So part C, at t equals 40, we get that S of 40 will be equal to 30 minus 30 e to the minus 40 over 600. Before I plug that into a calculator, I would probably simplify to e to the minus 4 over 60 or 2 over I might be trying to make it a little bit too simple. So 4 over 60 is the same as 1 over 15. So maybe that simplification step would have caused me an issue. Yeah, maybe let's make it a little bit, let's make it 2 over 30. So I can see that 4 over 60 is the same as 2 over 30, and that's easy enough to type into a calculator. And if you type it into a calculator, you'll find it is approximately, well, it's approximately 1.93, and remember the units, this is measured in milligrams. And that's really all I'd want for that question, just at this time, that's what we get. Now, this next part of the question, part D, is tricky. It says, how long does it take the level of pollution to fall to 0.002 milligrams per cubic meter after the toast is taken outside? Now this is tricky because this isn't the same system. You have to really look at what happens to the equation here. So I'm going to leave this number up for now. So for part D, after we remove the toast, the rate of change is now given by, well, the rate of change in the smoke level with time. Well, we've removed the source of the smoke, so all we have left is the air conditioner pumping smoke out. And that means we just remove the inflow part of the equation. That's minus S over 600. This is what the air conditioner was doing. It was taking smoke out of the system at this rate. So that. So maybe that's not clear enough, so I will clarify it, i.e. only the effect of the air conditioner remains. And I must say, many people got this wrong in the last exam. They didn't understand that when you remove the toast, all you have left is the effect of this term here. So that was a common problem. Now, this is a very easy equation to solve, because it's a very simple linear equation. I think you encountered this when you were modeling first order equations. It's really the model for an exponential decay. And because this question is quite long, I would be happy if people just went straight to saying, I know how to solve this. There are various ways you can get it, but This is a model for exponential decay. And solutions are given by, well, they're given by that the level of smoke will be some constant, I don't know yet, times a decaying exponential, in this case minus t over 600. And I'll just say what that is for some constant E. So I need to work out that constant E. Now that really depends on what are the initial conditions, and there are a few ways to work this out. My personal preference would be to start a new clock. So start at a new time 0 with the smoke level we had. Now I accidentally rubbed that out, but the smoke level was 1.93 milligrams per, just 1.93 milligrams. Right. So you don't have to do it that way. In fact, I might not, well, it's going to make my explanation slightly hard. No, I think in terms of the solution, in terms of the solution, it's still best to do it with a new clock. So if we set that the level of pollution is 1.93 at t equals 0, meaning so let me just explain what t is, where t is time in seconds since toast was removed. So here t is not the same as the original t. I've sort of reset my stopwatch and said time 0. So we set this to equal to that. The only reason I do that is it makes this quite easy. So we do that, we get, well, it's quite nice. If you put in 0, this becomes a 1, and I must get that E is equal to 1.93. So that's the reason I reset my stopwatch. If you don't reset the stopwatch, this number is a little bit uglier. You can do it without resetting the stopwatch. You can take time 40, but time 0 is much nicer. So you have to sort of say, I'm measuring now, that's 0. Okay, so we get that equal to that, i.e. the smoke level is given by 1.93 e to the minus t over 600. And that's just measured in milligrams. So very last part of the question, and then we're done with the exam, is how long does it, so I've solved the model, now I need to use it to answer a question. How long does it take the level of pollution to fall to 0.02 milligrams per cubic meter? Right, so this is our model. So it's really a question about density. So, and the question asks for Well, it wants that the density, which is S over the size of the room, so this is milligrams per cubic meter, should be equal to 0.002. So that tells me I'm looking for S is equal to 50 times that. So times that by 50, I get, well, first by 10 I get 0, and 2, times that by 5 I get 0.1. So I times that by 50, I think I get 0.1, yes. And in terms of the model I solved for, so if you didn't shift the clock like I did, this would be a little bit harder. And I'm going to get 1.93 e to the minus t over 600 is equal to 0.1, from which it follows that, well, e to the minus t over 600 is equal to 0.1 over 1.93. And finally, after working through all the details, so if you take the log and rearrange, you'll get that t is equal to minus 600 times the log of 0.1 over 1.93. And that is approximately, well, if you work it out, it's approximately 1,776. And I wouldn't leave that as my answer because, to be honest, well, firstly, this is measured in seconds. So I wouldn't leave that as my answer because it's not really understandable to me what that really means as a time. If you told me, let's meet in 1,776 seconds, I have no idea what you're saying. So let's just say what it is about, which, okay, means that about, well, if you work it out, it's 29 minutes and 36 seconds are needed for the level to drop, for the level to drop to 0.002 milligrams per cubic meter, which is what the question asked us to do. Yeah, so I mean that is correct, but it's not a human readable number. I think that's a much nicer thing to say. So that was the last question in the last exam. Now I was not the one who designed this exam, so I can't tell you how similar they're going to be, but they will be using a very similar scheme. They will be looking to see both whether you can answer the questions and how well you presented. Now do bear in mind that presentation is 5 marks, so it's 25% of your mark. So if you feel that it's kind of slowing you down trying to get all the exposition out, maybe you want to rush ahead with the calculations, because the calculations themselves are still worth a fair amount, but the questions are also quite hard. So yeah. At the very least, you know that if you if you're sitting the exam, you have passed the course, so you shouldn't worry too much about that. You've already passed the course. This is just trying to get a feeling for how well you know the material and can present your work. One thing I will say is, when I marked last year's exam, they do let us know when the students leave the exam room, and a lot of students left the exam room at about 45 minutes or 1 hour. I think many people may have been giving up. So please don't do that. You might as well just put the most effort you can in. If you finish a question and you have a lot of time left over, it's a good chance to read over what you've done. Maybe you can make small corrections, leave comments for the people who are going to mark it, say, try and fix up some of the any problems you might have thought about. So yeah, so good luck on your exam. It's very good for getting to the exam, and I hope you do very well.